So the first data type we're going to be looking at in the video is graphs. So these are sometimes called symbolic graphs, and it's essentially how you've structured your neural network. So if we take a gluon block, which is the base component for building your models in gluon, gluon being the imperative API for MXNet. Here we're going to create a really simple network. It's got 3 dense layers and we add them to a hybrid sequential block. So we need to make this a hybrid sequential block because before we give the graph to MXBoard, it needs to be hybridized, it needs to be a symbolic graph. So we create the hybrid sequential network and then we have to call these operations. So firstly we want to hybridize the network, and that's going to convert it to the symbolic graph. And we need to then initialize the parameters of the model. And that's a 2-step process with MXNet. First of all, you specify how you'd like things initialized. So here we're just using the default initialization. And this is lazy initialization, so then we pass some data through the network, and then it will infer the correct dimensions and the shapes for all the parameters. So that's what we're doing in the next step. We're just passing some really basic data through, just some ones of shape 1, and then that will calculate and work out the parameter shapes for us. So now we've got a hybridized block that has been initialized, and we can pass that to our summary writer. So as in the last video, we're using a context again, because this manages the opening and closing of the summary writer for us. We're logging the graph to this logs directory, which is in the logs folder, and we're specifying the run. So this is just the label that's going to be used. Open the context, we give an alias to the summary writer, and we use that straight away because we use the summary writer add graph method. And we can pass our net directly through, so the net that's been hybridized and initialized. If we run that code, it's going to store that data to this folder. We've got TensorBoard running in the background, so it should pick that up automatically, and then next time we go to TensorBoard, we should be able to see it. So with TensorBoard, quite often you need to refresh to get that update, and there is also an automatic update, but I find refreshing is more stable. So here if you click Settings, you can choose the refresh, reload data every 30 seconds. And actually in the background, it's just refresh that for us. So it's detected in the logs directory. Now we have the graph data, and we've got the run, it's called types example, so that gives us our label. So here we now have a visualization for our network that we've just created, which is great. If we zoom in a little bit, which you can do with the scroll wheel, we can see we've got some color coding that's appeared. This is automatically detected if it notices there's repeating structures. So there's some similarity between these 3 blocks and similarity here. So if we click on a block, we can see a bit more detail. We get the label of this particular block, and this is showing us that it's a dense layer, and we can even click the plus to drill down a little bit more. If we double click, we now get a more detailed look inside of the dense layer. So the dense layer has a few different components. We have here the bias. If we look at the label, we've got inside the dense layer, we've got the bias term, we've got the shape of this bias, so it's 128, and that's because we had 128 hidden units in our first dense layer. We've got the weights as well, and again we've got the shape specified. If it's a 0, it will still be calculated depending on the input. Those two are then combined, and that will give us our dense layer. In green, we have our ReLU activation. Double click on that as well, but we could just put the single item inside of there, and then this would continue all the way through with our data flow being from the bottom to the top. So now if we take a look at a more interesting example, we could take a model from the model zoo. Here we use Inception v3, which is used for image classification tasks. and we go through the same process. First of all, we want to hybridize the network, which is so we can create the symbolic graph, and then we initialize with the two-step approach, and we pass through an image of size 299 by 299 height and width, and then it's 3 channels. It's an RGB image. As before, we open the summary writer, create the context, and then we use the summary writer to add the graph. Note that here we're using the same log directory as before for the same graph, so it's going to overwrite the previous graph when we run this. If we run that now, move across to TensorBoard, we'll still get the same graph as before until we do the refresh or wait the 30 seconds. So let's just force a refresh. It's taking a bit longer to load this time because the model is more complicated. And there we go, lots and lots more layers than before. So let's just do a bit of investigating. If we scroll to the start where we have the data coming through to begin with, the very first layers that we're going through are just standard convolutional layers. We have batch norm layers, and then we've got ReLU, and this continues for a while. We even get the forks rendered. So this is an inception block where we've got multiple paths through the network, and we can see all those with different repeating structures. So again, if you were to click through, you can see the batch norms and the ReLUs and the convolutions again in each path. And we can see how they split and then get recombined, which is what we'd expect. You can do this for symbolic graphs using the symbol API, not just in Gluon. So if you are still not using the module API with symbols and you've got a symbol already constructed, you can just go ahead and use the summary writer to add the graph to TensorBoard as well. So here you'll notice we're using mx.sim, which is for symbol, creating the variables, adding all the layers, and the fully connected layers. So let's run that. Refresh TensorBoard. And then we see our updated graph using symbols instead of Gluon blocks.